Hello and very good afternoon, everyone. I'm Mohammad Tehrani, and I would like to welcome you all in the second session of the first edition of the Water Whispers Wednesdays webinars. This is a sharing time, which is planned to be held a couple of times during the year, sharing the hydraulics and water relevant issues. For those sessions where the speaker will attend in person, the webinar will be conducted in hybrid mode, and unfortunately, this is not the case this time. Each session will feature dynamic presentations lasting approximately 30 to 40 minutes, followed by an interactive 20 minutes of the question and answer session. Before we dive into the talk, a quick reminder to stay engaged, please. Feel free to ask questions using the chat box, and we will address your question in a dedicated Q&A session at the end, or you could turn on your mic and camera and ask your questions or share your comments directly. Today, there is no exception, and this is the second session of the 2024 series. We have a distinguished speaker who will share his expertise on AlpLakes, advancing lake research and management, integrative remote sensing and hydrodynamic models. Whether you are a pioneer, senior professional, or just a young beginner in this area, get ready for an engaging and informative session. And without further ado, let me introduce our esteemed speaker for today, Dr. Abulfaz Irani Rahabi, or the more appropriate pronunciation is Rahabi, if I'm right. Abulfaz holds a PhD in Environmental Science and Engineering from the École Polytechnique Fédérale de Lausanne, EPFL, Switzerland, followed by his first postdoc there, mainly focused on the investigating spatio-temporal variability of air-water heat exchange and lake surface water temperature using spaceborne and airborne products and 3D hydrodynamic models. Since 2020, he respectively has joined Swiss Federal Institute of Aquatic Science and Technology, AWAC, and University of Zurich as a senior postdoc, and has been involved in several research projects, including high-resolution SWT, retrievals, optical closure of aquatic reflectance, calibration and validation of remote sensing reflectance and water quality products, estimation of primary production from satellites, as well as integration of satellite products, 3D hydrodynamic models, and particle tracking. He will tell us more about himself and his projects. So without further words, Abulfaz, thank you so much for accepting to be with us today, and the floor is yours.
Thanks a lot. So I think if you give me like the presenter, permission, then I will share my screen. So I hope you can hear me well. Can you hear me well?
Yes, we do.
Hello. Okay. And do you see my screen? So I would go to the presenter mode.
Yes. Now also we receive your screen very well.
Okay, so everything is okay. So yeah, thanks a lot, Dr. Tehrani, for the nice introduction. So again, my name is Abulfaz Irani Rahabi, and it's a great pleasure for me today to present to you the AlpLakes project. Operational web platform for lake research and management. And with this platform, we are hoping that we can improve the interaction among scientists, stakeholders, and people, and ultimately have a better understanding of these very interesting environments. So again, I'm from Swiss Federal Institute of Aquatic Science and Technology, or AWAC, and University of Zurich. And this work has been done in collaboration between AWAC, CNR, and University of Toronto in Italy. And the project was funded by European Space Agency. So first thing first, I would like to introduce the AlpLakes team. As you can see, so we had in this project, we have people from different disciplines. On one hand, we have people on remote sensing, Daniel Odermatt and Mortimer Werther from EVAC, and Mariano Bresciani and Claudia Giardino from CNR Italy. On the other hand, we have people mainly specialized in modeling, Damian Buffard from EVAC, who is also or the project is finished, so I would use the past tense, who was the PI of the project, and Marco Tofolon from University of Trento. Then in the middle, you see we have Marina Amadori, a postdoc in Italy, and myself. So we basically did, I would say, most of the job. And the focus was to integrate remote sensing and modeling and in situ measurement. Last but not least, we have James Ronalds, who is a software developer at EVAC. And basically, he's an amazing job to translate, all the model and information from the backend to front end, and what you can see today is in the AlpLakes platform. So here, thanks to Dr. Tehrani, so I will skip most of the part here, but I just wanted to give you an overview of my background and especially my link to numerical modeling and remote sensing. So by training, I did a bachelor and master's in mechanical engineering at Sharif University of Technology in Tehran. It was followed by a few years of industrial experience and doing my military service. Then I joined during that time. So I should mention that I got some, knowledge on the fundamental and advanced fluid mechanics and numerical modeling. Then I joined EPFL to do my PhD, in which I started to explore limnology, and the project was my project was focused on air-water heat exchange. I also did airborne thermal remote sensing, and I started to dive into lake 3D numerical modeling. It was followed by a one-year postdoc at the same group, which basically my main job was to investigate the climate change impact on the temperature variation of a lake in Switzerland. Then I joined EVAC. So I got involved in several projects in which I had expanded my knowledge in remote sensing, and in particular remote sensing of water quality parameters. And I did some project on lake primary production, and then I got involved in this AlpLakes project, which the goal was to integrate remote sensing in situ and numerical modeling and particle tracking. Currently, I'm doing another postdoc between EVAC and University of Zurich, in which we are focusing on space-borne lake surface water temperature retrieval. And we would like to integrate these products in the future into the AlpLakes, as I will show later. So to give you some motivation and background, this image from a previous project shows quite nicely the sources of information in a lake environment, or more generally in a S system. So on one hand, we can get the information from 3D models or 1D models. So with this model, we will have a high spatial and temporal resolution, data, but we know that the models need, in situ measurements for calibration, and also they are imperfect. On the other hand, we had remote sensing products. Usually they are the resolution is less than, numerical models, but also they are sparse in time. But again, they are perhaps in terms of quality a little bit better than, numerical models, as they give the real measurements, but still they require, in situ measurements for calibration and validation. Last but not least, we have in situ measurements that can be, acquired from different, methods and platforms. Those are the most accurate ones, but they are sparse in time and in a space. Basically, in time, these days we have automated stations. So this slide somehow highlight the the link between remote sensing products and 3D hydrodynamic models. So let me go to the pointer option. So I would like just to emphasize, how remote sensing products can support 3D hydrodynamic model. So on one hand, they can be used for calibration and validation. For example, the lake surface water temperature can be used for this purpose. On the other hand, so the same product, like surface water temperature, can be used for the data assimilation of, the the numerical models. Other products like SekiDepth. SekiDepth is a proxy or a measure of the transparency or clarity of the water. So it can be used to, accurately model the light penetration into the water column and give us a better understanding of the thermal structure of the water column. We also have other interaction between remote sensing and 3D model, like, for example, SAR backscatter products can be used to improve the wind forcing. Wind forcing is, the surface forcing that ultimately is used to run hydrodynamic models. Or we can use the turbidity products to track them, in time and space and use them in particle tracking. So these are some examples of the link between remote sensing and numerical models. But what are our goals in the AlpLakes? So our ultimate goal is to facilitate a constant dialogue among models, remote sensing, and in situ measurements. Ultimately, so this is just the goal, but what do we want to achieve? So we want to improve the long-term and short-term investigation of lakes. And also, thanks to the weather forecast models, we also want to offer near real-time solutions. So in the AlpLakes, I will show later, we have a 5-day forecast, for example, for now that can be used, in case of some stakeholders, the need to predict what's going on in the lake. So what does it mean in terms of the interaction between remote sensing and modeling? So in most of the slides, I skip in situ, but in situ, please remember that the in situ is at the core of calibration and validation of both models and remote sensing. So what does it mean in this interaction? So we have two main objectives. One is the integration. By integration, under the AlpLakes project, I mean that we integrated SekiDepth or transparency products from remote sensing into our numerical models. Again, as I mentioned before, to have a better light penetration model. And then in terms of validation, we use the total suspended matter, or we can translate it in turbidity, as well as chlorophyll concentration in the particle tracking model to validate, what we observe from satellite and also from the model. So here I show the general workflow of the AlpLake and what's basically we have as the inputs and what we ultimately show as the outputs in the platform. So again, on one hand, we have in situ measurements like water quality and radiometry that we use for our remote sensing, calibration and validation. And here we basically work with Sentinel-2 and 3 sensors. So these are our current target sensors. And then we get SekiDepth product as well as total suspended matter and chlorophyll. SekiDepth product, as already mentioned, they are used, integrated into numerical model. Numerical model, they need in situ measurements, in our case, mainly temperature profiles for calibration. And also they need surface forcing. In this case, we use reanalysis data at 1 kilometer resolution run by Swiss Meteorological Office. And in terms of models, we have Delft3D, which is primarily used in our web platform, but we also have good experience with another model called MITGCM. Then this velocity field obtained from the numerical models, they used in the particle tracking. And in the particle tracking, we have online, two different approaches, an online and offline, which I will explain it later. And these are the final products that we'll present in the AlpLakes. Remote sensing products, particle tracking, and temperature and velocity from 3D model. So this is if you go to this website, to AlpLakes website, you will see that currently we have 12 lakes, and this is what you would see. So if you have not tried it, I would encourage you to go there and try, different lakes, different products. And yeah, there is an option. If you see an issue, please report it to us as well. So what are the available products and features on the AlpLakes? So if you click on one of those lakes, in this example, I clicked on Lake Geneva. So you will see something like this. And in terms of the products, the numerical modeling products, we have temperature, current, and thermocline depths. You will also see an advective simple particle tracking, which is online and very fast. And also you would see chlorophyll, turbidity, Secchi depths, again, turbidity from another satellite, and true color from both satellites. And in terms of the current features, as I mentioned earlier, so we have a 5 days forecast, and also you have the option to look at different transects or profiles at single points. So these are the current features. So now I would go into the different compartments of the AlpLakes numerical model, remote sensing, and particle tracking, and give you some of the challenges that we faced. So I would start with numerical modeling. So again, so these are our 12 lakes and the grids that currently used in AlpLakes. But here also you can see those lakes on this map. So these lakes, these 12 lakes, they have different morphological features, and they also, for example, they are at different altitudes. So it ranges from around 65 meters to around 2,000 meters. So they are quite diverse, and this has its own challenges. And the red dot here are the historical monitoring station that basically we used the water quality and temperature profiles for validation of our numerical model and remote sensing products. We also use other data set that I will mention later. So again, so in terms of the data availability, so we also have great heterogeneity among those lakes. For example, Lake Mora and Lac de Joux here, you see we have high frequency multi-year measurements, whereas in another lake, like St. Moritz here in the middle, we have only a couple of profiles per year, which makes it super difficult to calibrate a model for that. So, and then in terms of the approaches or performance metrics that we used, so we used root mean square difference of water temperature profiles and the Schmidt stability, which is a proxy of the lake resistance into complete mixing, I would say, in a simple word. And you see the formula here. And then what we did here, which helped us a lot, was we implemented an automated calibration tool called DinoPaths. So we used it, so we automatically calibrated the Delft 3D model for all those lakes, and we split the calibration into 2 phases, cooling and warming, but I won't go into the details. Here are some results for some sample lakes. On the left panel, you see the observation for, I think, 1 year. And on the right, you see the corresponding 3D model. So as you can see, we are more or less happy with what we obtained, the calibration of the numerical models. But again, in the lake, like Ageri and St. Moritz, we don't have too many profiles. And here you see the overall performance of our models, which is not bad, except like, for example, St. Moritz, which we think is due to lack of enough observation. Then I would give you a bit more detail about our remote sensing products. For example, here you see on the left panel, you see the Secchi depths for Lake Geneva during beginning of September 2021. I have some slides on that one. And on the right, you have Lake Garda, the TSM, total suspended matter for Lake Garda. And I would use Lake Geneva and Lake Garda a lot because these are like the 2 largest and deepest freshwater lakes in Western Europe. So there are quite a lot of dynamics inherent in those 2 lakes. So I would start with some the background of aquatic remote sensing and the challenges that we are facing. So on the left image here, you see the interaction of light and water. So the light that reaches the surface or doesn't reach the surface, the light that we have, so it has 3 paths. And one path is that the scattering in the atmosphere, which reaches the satellite sensor. Some part of the incident light, it gets reflected, and some part goes into the water, interacts with the constituents in the water in terms of absorption and the scattering. And after this interaction, it comes back to the surface through something that we call water leaving radiance. And all of this, they reach to the atmospheric, to the satellite sensor. What is the challenge here? So this top of atmosphere signal, which is sum of these three, is not what we are looking for. We are looking for water leaving radiance. So that's a challenge to disentangle this part from the other two. And this is done through something that we call atmospheric correction. And there are several methods for this. And in AlpLakes, we tried three of the most common ones and evaluated them and find the best ones for our test sites. The other challenges that we have been facing was this, direct versus inverse problem. So imagine that you have a dragon. So you know the dragon, then it's not that difficult to, guess the tracks of the dragon. So how do we translate into what we see in the aquatic remote sensing? So it means if we know what's inside the water in terms of like the particles, then it's not that difficult to understand what is the water leaving gradients, although it has its own challenges, but not that challenging, I would say. But the main challenge is you have the tracks and you want to guess the dragon. So it means, imagine that we have the water leaving gradients at the satellite. Then the question is how we can guess what's in the water. So this is super challenging, but it's done through biooptical or empirical models that we also use a couple of them here in the AlpLakes. So how it's translate into the workflow that we followed in AlpLakes. So again, we have these two main boxes. The left is the atmospheric correction that I mentioned, and the right is this biooptical or empirical or inverse problem that I already talked about. So for the atmospheric correction, so we have the radiometry measurements. AOP is apparent optical properties, which is like, it can be this water leaving gradients, for example. It comes, in situ data comes from the campaigns that we conducted in those lakes, as well as a few automated stations that I will show in the next slide. And then we get the same product through different atmospheric correction methods, in this case, polymer, C2RCC, and acolyte. So then we somehow look at the matchups and how they match to each other. And then for each lake, we can find the best performing atmospheric correction. So one of these three. So now we have this, water leaving gradients. Then the question is how to go through this inverse problem and find the water quality parameters. Again, we need the in situ data for calibration, validation, and reparameterization. So the in situ data came from the campaigns that we conducted, as well as the historical data that measured by the water protection authorities in all of those lakes. And then we reparameterize, and then we find the final products that you can already see on the AlpLakes. So these are the automated stations that I mentioned. So we had three of them in three of our test sites, Lake Geneva, Lake Garda, and Greifensee. So, and basically we have several sensors in those lakes, but the ones that we use are water inside Wispa Station and Ipstar from those lakes. And also, as I mentioned, we also conducted some field campaigns that we use the handheld WISP to measure that water leaving gradients in situ that we used later for matchup analysis. Here, I just want to show you one example of this, the second part, the inverse problem or the biooptical calibration that I mentioned earlier. This is for Secchi depth or transparency product for Sentinel-3. And we use an algorithm which is called QAA. So here on the left, you see the remote sensing Secchi depths as against in situ data. And if we use the original parameterization, you would see these gray dots. But we, as I mentioned, we had to recalibrate those models. After recalibration, this is what you see in these, colored dots. And the same product, but for like time series in Lake Geneva, in one station in Lake Geneva. So the black dots are measurement. The gray ones are the original parameterization, but the blue ones are like what we recalibrated for that lake. So with that, I hope I could, show you some of the challenges of remote sensing. And then I would like to give you an overview of our particle tracking. So here you see this nice animation from all these 12 lakes. So this is basically a test, that's proof of concept test that we run for 5 days in all of them during summer 2022, I believe. And I want to show you what's behind this. Or first, I would start with the concept. So imagine that you have a TSM or color film map on day 0 from a lake. Again, I use Lake Geneva because of high spatial variability. Then we convert this map into the particle. We have some scripts that do this, and they are openly available for you. And when we have the 3D numerical models already integrated with Seki depth data, then we would use the velocity field from that model. We will track those particles in time and space, and then we will reach to day 1, day 2, and so on. So then the question for us would be the ideal case would be if we compare that, the following days with the following satellite products, so we expect that they match. So it's very difficult to get that, but you have to do lots of, I would say, trial in terms of how you see it, your particles, and also a little bit of, recalibration of 3D model for some specific cases. So this is the concept, but what are our approaches? So we have 2 approaches, as I mentioned earlier. One is very simple online approach, which is advective. It's 2D, only horizontal. It's good to get a first grasp of the particles' movement in the lake. It's only available in forward. By forward, I mean you just can track the particles in time, in forward in time, and see the fate of the particles. There is no way to understand the origin of the particles or where do they come from. So there is not much flexibility in post-processing, but we also have an offline model, which you can find the script here, which is much more flexible. We have a script to convert the satellite data into particles, available in both forward and backward, and this is based on a model called TrackMass, or C-Tracker in our case, that they are equal. And then it's very suitable for detailed scientific investigation. To give you an example of the difference between them, I took this example again from Lake Geneva. If you go to the AlpLakes and go to this date from summer last year, you would see that there is a hotspot TSM here. Okay, if you follow the map in time, this is from Sentinel-3 product, you would see that this hotspot, it would follow the northern shore, and then after a few days, it will come back to the southern shore of the lake. So here you see the 2 approaches. The simple online model, if you release some particles, they will go follow the northern shore, but they will ultimately end up to the western part. Whereas if you use this, I would say, more sophisticated offline model, you would see that they go again, follow the northern shore, but at some point they come back. It's a bit more, at least for this case, it's very closer to the observation. So this is what I'm trying to tell you. So maybe offline is better for detailed scientific investigation. So I'd like to now give you some science use cases of AlpLakes. So I would give you some slides on this Ruglena bloom in Lake Geneva, few slides on resuspension event, and few slides on the potential application that we are currently conducting basically in Lake Geneva. So in the beginning of September 2021, so Lake Geneva experienced this unprecedented, Ruglena bloom. Here you see the microalgae under microscope. And the lake, as I said, so it's people around the lake, they could see this really brownish, unique, color of the lake and, the odor of fish. But just to give you like how serious is this issue. So this is typical Lake Geneva. It's oligotrophic lake, so usually very clear water. So that was a bit shocking for people. So because of this, it went very quickly into the news. Sorry, these are all in French. But just if you look at the date, so this bloom happened, on September 6th. But if you look at the news, so they are more or less in the same day or next day or a few days later. So this means that, there's an urge for a very fast action on such a unprecedented event. So we started AlpLakes on 1st of September 2021. This bloom happened on 6th, so 6 days after the kickoff of our project. So by the time we didn't have a platform, but we found it very unique opportunity. Then we looked at the remote sensing signals. So on left, you see the color field concentration from Sentinel-2, and on right, the Secchi depths from the Sentinel-2. Again, so you could see some striking spatial patterns like this mushroom-like structure or these gyres that are obvious here, or some patterns evolving from here. And the values are really, really not seen before in Lake Geneva. This bloom, Uruglena, was only reported in 1999. I will get back to this later. Then we ran a high-resolution model for this event, and we looked at the model results. On left, you see the vertical velocity averaged a few days before the onset or the peak of the bloom, I would say. And as you can see, so the more reddish, it means the higher the vertical velocity to the surface. So it's already a sign of an upwelling, coastal upwelling a few days before. If you also look at the transect P0, P1 here, you see P0, P1. So these are the temperature profile, again, from the model. And as you can see, there is also a tilting of, this is thermocline, that so it's tilted towards the surface, again, a sign of the coastal upwelling. So this is the second information that we got, so from the numerical model. And based on this information, we started to run a particle tracking. So we released some particle in the southern shore at the place of this coastal upwelling, both from the model and from the satellite. And then we tracked them forward in time. As you would see, so after a few days, we could reconstruct, I would say, some of the patterns, especially these mushroom structures, and some of the evolving patterns from the shore here. But also, we also could explain, this gyre. So if you need more, information, I encourage to check this newly published paper on this event. So this is, we were happy somehow with this particle tracking, but we didn't stop here. So we started to formulate a hypothesis for the emergence of this bloom. So we looked at the meteorological condition. This is the blooming. If you looked a few days before the bloom, we have a very calm and warm condition. And then immediately before this one, we had this strong wind event, which basically was driving this coastal upwelling that I showed you before. But again, year 2021 wasn't very exceptional in terms of summertime, but we had a flooding event in Switzerland, and especially close to Lake Geneva. So these are the water level anomaly for Lake Geneva starting from 1998 to 2022. And as you can see, there is a few hot spots. One is here, and the bloom happened here. So it was a few weeks or months before the bloom. And again, as I mentioned earlier, there was also Uruglena bloom reported here in 1999 during end of July, beginning of August. And we see this anomaly here. So it was already a hint to us to go and do some, long-term analysis. So we did that. We looked at the long-term meteorological conditions. We tried to come up with some mathematical and statistical, formulation of the probability of each of those three driving meteorological events. So on top, you see the precipitation. So these are the measurement data. And on top, you see the probability of the high precipitation, for example. The blue, the darker the blue it is, it means, the probability of having high precipitation a few weeks before is higher. And then we also looked at the wind energy. Again, similarly, I think you barely see some of the events with the high probability of a strong wind. And also we looked at the calm and warm conditions, which are, much more probable than the other two, conditions. So when then we combine these probabilities, basically just multiplying the values that you obtained here in this tree and just multiply them together, you would find the bloom occurrence probability. And surprisingly, this was only high during 1999 and 2021. So the rest of the years, it was a bit, low, which, these 2 years are the years that Urglena bloom was, reported. What is the message here? The message is the sequence of meteorological condition matters. So not only individual conditions matters, but also the sequence is important. So again, if you want to get more information, please do not hesitate to check this paper. Another, application is resuspension events in Lake Garda. Lake Garda, especially in the southern part here, so it's very shallow. When there is a heavy rainfall followed by some wind event, usually they experience some resuspension event in the southern shore, as you can see from all these Landsat and Sentinel-2 satellite images. So the idea was, if we can somehow reconstruct, such suspension events. So we used the hydrodynamic model. Actually, my colleagues in Italy, Marina, started to look into that. So they ran some forward particle tracking, meaning they, looked at, the map on 15th of November in one of the occasions and tracked them forward in time. So they could somehow get what they see here, but still it can be improved because, the models that you see here is with 400-meter resolution. So now they are trying to do it with the model with 100-meter resolution. And we think that will improve the results. They also did the same exercise with the backward tracking, meaning so they looked at the pattern on 24th of October in another occasion, and they tracked them backward in time to see if this observed pattern on 24th is basically the same on 16th, an evolution of the one on 16th of October. So here you see the map of the frequency of the particles passage, which is, again, somehow similar, but still it can be improved, and they are working on this one. Another application is, tracking the origin and distribution of metalimnetic methane in Lake Geneva. Group at University of Lausanne, they took some, samples starting from here. This is called Rhone River, which is the main inflow to Lake Geneva. So they took some samples at different depths. They followed this station 1 to 5. And then they asked us if we can somehow help them to find the origin of, what they observed. And their main hypothesis was basically it's perhaps coming from the Rhone, from the main inflow. So we helped them with some particle tracking model. Also, I think it was last year that they wanted to do some sampling, and they asked us to help them to pinpoint, the hottest spot for sampling, basically. So we use our forecast model. So we tracked the particles from the Rhone in time forward, and we told them, yeah, look, for example, it seems that this part of the lake is most probable in terms of following the main inflow from the Rhone. Similarly, another group at EVAC, they are working on tracking the fate of bacteria released from a wastewater treatment plant. So here is the city of Lausanne in top, and wastewater treatment plant outfall is somewhere like here at 30-meter depths. So what we did for them is we released some particles for the specific time that they were interested in. So we released some particles at this wastewater treatment plant outfall, and we track them in time. With this slide, I just want to show you like how dynamic is this lake. So if we track the particle above the thermocline, like closer to the surface, they would go mainly to the eastern part of the lake, and they will follow this big gyre. But the particles in the deeper part of the lake, they would go like to the western part. So it means these tools, they can simplify the complex dynamics. Again, they also wanted to give them some, potential sampling location, which again, we use our forecast models to help them. So this is another, application. With that, I would like to conclude and give you a little bit of outlook in this project. So what AlpLakes and similar web platform can offer. So we are not the only, operational web platform. There are some others that you can find, but they have different, size. They have different features. But in general, they can combine information, and especially in our case, so we combine in situ measurements, remote sensing, reanalysis, methodological data, and hydrodynamic models. We can also combine tools and give an easy access to the people who are interested in. Again, I would repeat, scientists, stakeholders, and also people like local people especially. So the tools are 3D models, particle tracking, remote sensing pipeline, and automated stations. And as I showed, I hope I could convince you with some of the examples that I showed that it can also foster the collaboration and knowledge exchange among different, disciplines. So here we are talking in lakes, we are talking about aquatic physics, biooptics, biogeochemistry, ecology, etc. So this is the opportunity that we hope we get from AlpLakes. And again, there are still lots of room for improvement. What we are doing now, we are trying to add more lakes to the platform. They are underway. As I said, now I'm working on lake surface water temperature retrieval, and we hope, like perhaps in a year or two, we can have them available on AlpLakes for all those lakes and more. And then the particle tracking that I showed here, track mass based, is the particles are inert. So there is no decay, growth, or sinking. So we hope that we can also include these features to this particle tracking module. And another issue that we have with satellites is, especially in the optical and thermal band, when there is cloud, so we cannot get satellite data. And this will limit our data set. So what we are thinking is maybe, this particle tracking can be used for gap filling as long as we are, happy with our products. With that, I would like to thank you all for your attention. And I have to emphasize here that we strongly believe in open science. So you have access to all the codes, all the data openly available. And if you have any questions, suggestions, please send me an email or my project partners. Yeah, thank you very much. I would be happy to take some questions.
Great. Thank you so much, Abulfaz, for your enlightening and very interesting presentation. We enjoyed it, and also very good timing as well. Yeah, perfect. So for the moment, I think I have asked already of the audiences if they would like to share comments or ask questions, please write them in the chat box. We have already received 3 of those, but in continue, we can also have them. I mean, if you prefer to ask them directly, we can do so. For example, Mr. Masoud Agha Mohammadian or Mr. Mohammad Zapezishki, or I can write. I mean, I can read it for you.
It's up to you. Yeah, you can speak out, or you can read them, and then I will try to address them.
Mr. Agha Mohammadian, if you would like to ask a question directly, you may make on your mic, or perhaps cannot have.
Oh, okay. You can read it. If
I will start with the first 2, and then we will see for the next ones.
Yes. Do you have my voice?
Yes,
Can you hear
yes,
me?
yeah.
Great.
Yeah.
Yes,
Hi, how are
we
you?
do hear you.
Yes,
Fine,
good.
fine.
Very nice
Go ahead,
presentation.
please.
Really enjoyed it. So the first question is, why wouldn't you use AI for the dragon problem? I think that would be very cool. It's like a textbook
Yeah.
application of AI.
Yes, yes, yes. Actually, this empirical, you see my screen now?
Yeah.
Yeah, these empirical models that I mentioned, we use biopticals, but some of the empirical models, they are AI-based, and they use neural networks. Also here, also in atmospheric correction, there are some AI-based models, which we tried. Those for atmospheric correction, they weren't suitable for our, test sites. Also, C2RCC actually is also AI-based. So this C2RCC is AI-based. But
Okay.
also, as I mentioned, we also have some empirical models which are AI-based. But again, we had some good experience with like these, algorithms. So we were happy with what we had, and we didn't try. We didn't want to complicate stuff. But thanks for a very nice question. And yeah, there are many models that you can try for. Maybe they work for your own sites.
Yeah, it's just it seems suitable for that application. And the other question that I had is that why go with satellite images? Why not try and install some sensors, some cameras just on top of the lake at a good view? I don't know. It's just your call.
Yes. Yeah, there are, again, thanks for the insight. We tried this for Lake Geneva. There are, we had some cameras somewhere here. We have put some cameras here. We could put some cameras here. So there are a few problems. First of all, getting the permission for all the lakes is very difficult, especially in Switzerland. Second of all, maintenance of those cameras is really painful, and we experienced this. And lastly, but not least, the cameras usually, like, for example, you put a camera here on top of a mountain, but it only covers like this 1/10 of the lake. Yeah? But like in satellite products, they are operated, by some big institutes. We usually have much less issues. We have other issues that I already mentioned, but not in terms of operating them. Yeah, and on this note, I would like to add that currently there are there is a trend towards higher resolution satellites, and those are on our radar. I'm not sure when we will be able to have them operationally on our platforms, but hopefully in the future they will be available for everyone. But again, thanks.
I really appreciate it because just like a couple of days ago, someone came to me. They had a problem. They wanted to, monitor some lakes, and I proposed that they should install cameras. And now I joined your presentation, and I see that you can use satellite images. It's excellent for me. I'm gonna steal your ideas, actually.
Yeah, no worries. No, we like to collaborate. If we can help, please approach us.
Of course. Thank you.
No
Good luck.
Yeah, thanks.
Great, thank you, Master. Thank you so much for those two interesting questions, which made the debate, and also thank you for Abultas. Thank you, Abultas, for addressing these two questions. Any other question from the audiences?
I see another question from Mohammad Reza Pezeshki. I don't know if he wants to ask it directly or.
So Mohammad Reza.
Okay,
perfect. So
I can read it.
Okay,
so
perfect.
That was amazing. Okay. Thank you. You're welcome. Pleasure. What was the computational power required for FIDES forecasting of the offline model? So it depends on the lake and the grid that you have, both horizontally and vertically. But this is not a big issue for our operation. I cannot give you the number, but really it's not an issue. And now we have more or less a powerful machine that we are running our model on that one, and there is absolutely no problem with computational power. And actually, we are thinking to go towards, higher resolution models. For example, the model that you see on the AlpLakes in Lake Geneva, for example, I know the Lake Geneva because I did that. So it's 300 meters, but I already, the results that I showed here, we had to switch to 50-meter resolution, which was really, time consuming. So we are thinking into going into like high resolution models, but I see the point, but I'm not sure if that's an issue. So for the models that we have, the computational time was not an issue. And 5 days of modeling on my machine, which is a normal laptop, it takes like, I would say, a few hours. But on a powerful machine, I think it's nothing. Yeah. Thank you for the question.
Yeah, great. Thank you so much, Abulfaz, for addressing this question as well.
Yeah. Yeah. Do you think there is like other questions? Please just either speak up or write it in the chat. I would be happy.
Yeah, that would be great. But meantime, perhaps I can ask my question. I mean, at least one of those.
Yes, please.
Thank you so much for your presentation. My question was that, okay, you use your particle tracker inside the lake, and also using the images from the satellites. So your findings and your model, is it compatible with different scenarios and different conditions, I would say, rather than the Europe? I mean, in any lakes out of the Europe, for example, in Iran also, or it will need some calibration or any consideration to be done before applying your model?
Yeah, I'm trying to find the right slide. Perhaps this is the right slide. Yeah, I hope you see my slide now. So generally, setting up a model, getting the satellite product, and running particle tracking for any lake now should be easy, and we can help. If you need any help, we have some instruction how to set up the model. And for remote sensing, for example, we have some pipeline here. I already put it here. Maybe, for Zencast, it's somewhere here. So we also have, we started to generate the Docker for simulation. So this is also amazing. You don't need to compile the code. It would be much easier with some instruction. So I personally don't see any big issue in setting up a model, for example, for your own, or getting the satellite product for your own. The main challenge would be calibrating and validating those products, so which requires in situ measurements, as you can see here. So for satellite, we would need some water quality or radiometry products. So if you have them, then the procedure is more or less straightforward. So, but this step is a bit challenging, I can tell based on my experience. And again, from for numerical model calibration, again, you need some measurements, especially some multi-year or few profiles per year in a lake, the temperature profile in a lake. So this is the minimum requirement. And then when you have this one, based on these tools that I mentioned, DinoPods, which is again publicly available. We also have some instruction on how to use it. So it shouldn't be difficult to set up your target function and calibrate the model. So that's my feeling, but I mean, we have to see.
Yeah, perfect. I appreciate. Meanwhile, as we do not have no other question yet, perhaps I can take the time for asking another question.
Yes.
Okay. What about if we have the area that we do not have that much of information or data from that? I mean, for example, the sensors that you use, perhaps in some areas we cannot use it
Yeah.
for different reasons that we would imagine. So in that case, is it possible to use, for example, AI for going from what we have already from a area to another area, or is there any other solution that you could go with?
AI, I'm not sure, because for AI still you need training. Training means you need data. So if you have data, so you can start with this, I would say physics-based approach, and then if you're not happy, you can go to AI. So I don't know if AI would be, at least I don't know how you want to do this, let's say transformation from one area to another area.
I see.
Another point is that comes to my mind is, for example, so these radiometric measurements, they are not usually done. So it's it's a bit more expensive. Whereas like taking Secchi depth or TSM or color field, this is very established and I would say much cheaper. So what you can do is there are some hints in the literature, for example, which can gives you based on your water type, your lake or optical water type. If I want to be more precise, you can select one of this atmospheric correction already. So you can skip this part and then try to focus on the second part, because ultimately what we are interested are these products. So you can skip this and then like Secchi dips is very cheap. You can also build it yourself, so it's not that difficult. Yeah. So this is my perception to go to another area. Otherwise, you can run it and then, like, for example, focus on just say, for example, if you have a model, you can say my model just capture precisely the spatial pattern. So we don't know if it's precise for the detailed values. So that would be also justified, I would say. Yeah.
Okay, perfect. Thank you so much. I appreciate it.
Mm-hmm.
So I think we still have time, if perhaps for one or more two questions. Meanwhile, perhaps it's good if I tell the audiences that at the end of the session, which will be in a couple of minutes, we would like to take a group photo. So prepare yourself for turning on your cameras. So we will have it together. Would like. Yeah. Waiting for any other question.
While we are waiting, I can also please, if you want to have these slides that I showed, please just send me an email, and then I will send you the slides. So there's nothing hidden there. So
perfect. So those who are interested in receiving the slides of today's presentation, please contact directly to Abulfaz, and he will share kindly his slides with you. And just perhaps to be mentioned here that those are interested in receiving the certificate. This would be free, but it needs your registration and the let's say links that's provided on the flyer. So you have to fill it so that we will have your email and the other characteristics to issue the attestation of let's say attending to this session. Yeah, perfect. Okay, I think for the moment we do not receive any more questions, and we are almost at the end of the time of the session. So those who would like to make a group photo, please turn on your camera. And meanwhile, if Abulfaz hand me, yeah, perfect. Yes. Please stay tuned for our next session, which will be in July, and the other which will be in October. The next one would be on the numerical modeling of aerodynamics and water quality, which will be presented by my dear friend Sayed Abbas Hosseini Saadabad, senior researcher from INRS Canada. Yeah, and please stay tuned and be be linked to us, and you can follow us on the LinkedIn. And the record of the session will be uploaded on the channel, YouTube channel, and also our channel for those who are interested to watch it again, or perhaps if you have missed something, you can follow it up later. Perfect. So please turn on your cameras, those who are interested to make a group photo. Yes, please, Abulfaz, go ahead. Yeah, we can hear you. I think we lost you for a couple of seconds. Yeah.
Yeah, that was perfect. Good. That was towards the end of the session, so I was worried in the beginning. So good timing.
Yeah, it has a good timing. It's just at the end of the seconds. Perfect. So I asked for those who are interested, but it seems nobody are interested. Perhaps Mrs. Bakhshande, Mr. Mirkli, or any other of those friends from KNTU who would be interested in making their cameras on and take a group photo. Perhaps they are not. Okay, no worries. Okay. Okay, yeah, sure. It has some delays. Perfect. Okay, we just wait some seconds if there are anybody else who are joining us.
Yeah, people are joining.
Okay, good. So waiting some seconds. Yeah, perfect. So I asked also Mrs. Bakhshande and Mr. Mirkatuli to do the screenshot as well as me. I will do that. Okay, let's count. 3, 2, 1. Okay, to me would be fine. I hope that we took the good screenshot here. Okay, thank you so much for your participation in this webinar as well, and a special thanks to Abulfaz for being so kind and accepting our invitation and allocating his time and sharing the invaluable insights about the lake monitoring with integration.
Pleasure.
Different methods and material. It was my great pleasure for having you here as well.
Yeah.
Perfect.
Yeah, thank you very much.
And we will be in touch. Yeah, thank you so much. And yeah. I think now you could go to lunch. Yeah.
Yeah.
Thank you so much. Yeah, perfect.
Yeah, thank you very much. Have a nice day.
Thank you. Have a nice day. Bye. Bye. And goodbye to everybody. Thank you so much all.